Welcome to our next video in the series with regards to demonstrating how EKS Anywhere and PowerFlex could work together with CSI integration, and at the same time being able to establish a hybrid data plane between a PowerFlex system which is hosted inside of AWS and a PowerFlex system where EKS Anywhere was integrated inside of Equinix. So as of the last video, what you would have seen is that we have established what is called as a replication protocol between the PowerFlex in Equinix and the PowerFlex hosted in AWS. With that said, we've also created what was called as a RCG, as you can see it on screen, a remote consistency group. And we have added to that RCG a volume pair, the source volume being the MySQL persistent volume on which we have a sample data set, and a target volume at the PowerFlex AWS system, which was created as a auto provision volume based out of the replication affair. Now, with that said, the current state, as you can see it on my screen, and you would recall it from the previous video, is that we have a protection peering. This is the Equinix hosted PowerFlex, and you can see that the remote peer system is in a state connected, and likewise I can observe the same at the AWS hosted PowerFlex system. So both systems are connected. We also have, as I said, a RCG, remote consistency group, called as replicate. And inside of that, I have a volume pair, a replicated volume pair with the source volume, which is our PVC, and the peer volume, which is also a volume that's yet not mapped to any Kubernetes cluster or any host inside of AWS, but it's just a volume inside of the PowerFlex AWS system, okay, without any mapping as such. Now, let's also recall that we do have a data set. So as of this date, the data set has also been replicated, which means the table car, which was populated with certain data, should also be available at the target volume. But in order to visualize this, while I can see it from a GUI that the replication state, as seen in the RCG, is consistent, which means that the data has, has been replicated fully. But for us to kind of be sure that this is what it is, I need to see the actual data at the other end, right? How do we do this? So at the target end, which is the AWS PowerFlex system, this volume, which is actually presented as a replicated volume, can be leveraged by, let's say, an EKS cluster. Like how we have integrated an EKS Anywhere cluster with PowerFlex on premises, we can also create an EKS cluster and create a CSI integration between that particular cluster and the PowerFlex AWS system running, on top of EC2 instances. So what we're going to do in this particular video is create an EKS cluster and deploy the CSI drivers so that it can talk to the PowerFlex AWS system running inside of AWS. Now, how do we do this actually? Given the fact that if I look at how EKS as such deploys its nodes, it runs a particular operating system which we can't can't tweak and can't work with in terms of customizations. Now, you know that in the nodes that run within the EKS cluster, on those nodes, we need the software-defined client, which will talk or enable those nodes to talk to the PowerFlex system. Now, this client is very specific to PowerFlex. It's called as SDC. It comes in various flavors, Red Hat, Ubuntu, any Linux and whatnot. So in this case, what we are going to do is when we deploy the EKS cluster, we are not going to use the standard or the default OS and AMIs. We are going to use the Ubuntu AMI, which from Canonical, they have given it as an EKS compatible AMI to start with as the baseline AMI. So if I look at my GitHub repository here. This is the EKS Anywhere GitHub repository. Inside of that, the PowerFlex folder, and I've made a short documentation around how to kind of create an EKS cluster with custom AMIs. Why custom AMI? As I said, we need to be able to install the SDC client inside of that, and certain packages that are required for this particular communication to come true. But before we even go there, in this particular case, my EKS cluster is hosted inside of private subnets. Number one. Second, it's linked together. The AWS and the Equinix are linked together through Direct Connect that enables private network. So there are certain prerequisites as to the steps involved in creating these private networking services. Number one, I will be tagging my subnets in which the EKS cluster will be created through a key value pair, which is shown here. Second is any services that would be deployed. And in this particular case, it will be the Adminer Web UI, which will work with the MySQL database that we will see on EKS in public cloud, that is AWS Ireland region. They have to be tagged, those particular services have to be tagged with these annotations so that I can use internal load balancers as opposed to external load balancers. With that said, you can create EKS clusters in many different ways. You could use launch templates, or you could use CloudFormation, you could use Terraform. My personal favorite is still EKS CTL. So I would be using EKS CTL to create this cluster. What EKS CTL would require is a cluster template, obviously. And this particular template that you see is a YAML construct. And in this case, specifically, what is of particular interest is the node group that I'm creating for the cluster nodes. They are booted with this particular AMI, which is provided by Canonical as a Ubuntu EKS compatible AI, number one. Number two is that I have to ensure that private networking is true because this particular cluster is going to be in the private subnets. Third thing is that if you read the note from EKS CTL, which I've pasted the URL here, there is a certain way to kind of configure the override bootstrap command so that the cluster rightfully boots up into the necessary environment actually. Okay, so you would see that there is a certain bootstrap script that needs to be presented with certain arguments. And you could read more on this URL, but this is how a cluster, which is presented through a custom AMI in a private subnet needs to be configured. Okay. But beyond this, I'm also supplying or downloading this particular script, which is a user data from my end to ensure that whatever OS packages, and you could just browse through this URL, it's there in the same GitHub repository under the PowerFlex folder. This script has the necessary routines to install the prerequisite OS packages, the SDC client installation, and the SDC configuration, so that it knows the IP addresses of the PowerFlex cluster in AWS and can communicate and establish that protocol connectivity. So long story short, we are going to build this EKS cluster and then validate if it can indeed connect to the PowerFlex AWS cluster. Okay, let me copy this particular template and I will hop over to, let's say, this terminal and export a variable for my cluster name. Let's name this cluster as, let's say, MCX AWS Demo 1. Okay. Now, let me also create a directory for this cluster name. so that my kube config and other things can go there. Okay. Now, I'm just going to build the YAML inside of that directory that I just created. And you can see that this particular YAML file holds my cluster configuration that EKS-CTL will use to create the cluster. Okay. Let me also go and run the command to say that create this cluster with this YAML, and this would be the kube configuration where it will be stored. Okay. Now the process as such would take roughly 25 minutes odd. So I will be pausing this video and then resuming it when the cluster is fully configured, up and ready. Okay. Let's run the command to create the cluster. As I said, this is going to take some time. So I'll be back in 20-25 minutes. Okay.
Recording.
So at this stage, we can clearly see that about 25 minutes into the run, the cluster in AWS, that's the EKS cluster, named MCX AWS Demo 1 in my Ireland region is ready. Okay. So now that the cluster is available, the PowerFlex cluster is available, the next set of obvious tasks would be to actually deploy the CSI drivers on the EKS cluster. Before we get on to that, let me just verify if I can see the nodes. Okay, so these are the two nodes on which my EKS services are running. Okay, these are the two worker nodes. Again, these are the IPs and the region, blah, blah, blah. Okay. Now, also, since the cluster was bootstrapped with the SDC client, these two nodes should be seen as hosts on my PowerFlex AWS cluster. You know that the SDC client on these two nodes would have initiated the protocol communication to the PowerFlex AWS cluster. And by virtue of that, they should be seen as hosts in the GUI of the PowerFlex AWS cluster. Let's validate that before we move ahead. And for whatever reason, if there is a challenge, you'll have to deal with that. Okay, let's see. Okay, so this is the PowerFlex AWS GUI. Let me log in. Okay, let me go into hosts. And we can see here, forget these two for that one. I will just remove them. So let's look at these two IPs, .92 and .174. And these IP addresses are of the SDC clients. And by virtue of what we've done, you should be able to correlate these two IP addresses with my cluster nodes here. You can see .92 and .174, and they exactly match with these. So you know that the EKS worker nodes are now talking to the PowerFlex AWS cluster. Okay, that's just the SDC communication. I mean, we still haven't installed the CSI drivers for the containerized workloads to be actually leveraging the PowerFlex AWS cluster. Now, what we will do is, in order to deploy the CSI driver, like we had done it on the EKS Anywhere cluster, we used a small minimal script that automates the CSI driver installation. the same script or a similar script with some tweaks specifically for AWS. I will be running it on the EKS cluster here. So let me log into let me go into the cluster directory, and I'm gonna just fetch that script from my GitHub repo. Okay, you have equal access to this. So I'm gonna go here, EKS anywhere. I'm gonna roll down to PowerFlex. And this was the script that we used for the EKS Anywhere CSI driver deployment. And there's another script called as install PowerFlex CSI driver on EKS-AWS. So I'm gonna pick up this, get the URL for this, and download it here. Okay, let me make this script executable and then run this particular script. Okay, I will supply the cluster name. In this case, it is MCX AWS-demo-1. I will provide the CSI release number that we will be working with. I will enter the GUI IP address for the cluster, and recall that our PowerFlex cluster in AWS has 3 SDS nodes or software-defined storage nodes. I'm going to give the IP addresses of those .124, 172.26, 2.125, and 172.26.2.126. Let me read it again. 124, 125, 126. I will also need the system ID of the PowerFlex cluster hosted inside of AWS, and I've already made a note of it here. So I'm just going to copy it from here. Okay. Let's paste it here. Let's give the credentials. And we also, like in the case of EKS Anywhere, we decided to install the CSI drivers on the MD0 node pool. In this case, although there are no separate node pools, but I've labeled the nodes in the same way as I did for EKS Anywhere nodes, which is group equal to MD0. Likewise, the same thing is happening here. So I'm just going to provide the node selector group name. That's MD-0. And what begins now is a quick run or installation of different components, which will be required for the CSI driver. Ultimately, we should be able to see the state where the controller and the node pods for the CSI drivers come through and deploy successfully. So I'm just gonna do yes. Okay. Oh, that's okay. I think the SSH so we'll just wait for the controller and the node pods to be ready. Let's give it a minute or so. So for whatever reason, the script would have either there could have been a SSH issue or whatever, but ultimately what we see here is that the VxFlex OS controller node pod or controller pods are ready. It's a success. The daemon set for the node driver pods is also a success. Okay. Plus, in addition to that, a PowerFlex storage class has been created, which will use the drivers, node drivers, to deploy any persistent volumes. And a snapshot class also has been created just in case we decide to take snapshots at this end also. Now, let's validate this by running kubectl get pods -n vxflex os. This is the namespace for the CSI driver. And as we can see, 2 controller pods. And since we have 2 nodes in the cluster, so there are 2 node pods also running as a daemon set. Okay, which means you have the EKS cluster, the PowerFlex over AWS cluster, the storage part, and the integration between these two through the CSI also complete. Now, on a different day, if you wanted to now deploy a workload directly on EKS, which is persistent in nature, you could start by deploying persistent volumes and the required workloads, and they will get deployed on the PowerFlex over AWS. So that's a different use case where, let's say, you have our Apex block over AWS offering, the underlying technology being PowerFlex, and you want to start deploying, instead of on EBS, you would like to deploy workloads on PowerFlex over AWS. Now, that's also a very important solution where performance is really monstrous actually, right? And there are enough reasons as to why you would consider doing that. In today's scenario, we're considering a different use case. You already have a persistent volume on premises in EKS Anywhere, and you have a replication pair out of which a volume has been created in the PowerFlex over AWS cluster. Now, that volume has not been mapped to any specific host, means it's basically on the storage, but it's not consumed in the Kubernetes cluster. So what we are going to do is basically build a persistent volume out of that particular volume inside the PowerFlex over AWS cluster. Okay. Now, you could envision the scenarios under which you would like to do that. Like what we spoke about, that from a ground to cloud perspective, for example, where this replication is from Equinix to AWS, you could be foreseeing a DR requirement in the cloud or a migration requirement or whatever it is. And we will now simulate that particular action, let's say one of the use cases, right, where you would like to do a cloud DR. And like I said, while the replication is being done from Equinix to AWS, if you wanted to do a workload repatriation or some kind of on-prem DR, the entire setup and the scenario would have reversed, where you would have the primary workload running inside of AWS in EKS, supported through PowerFlex over AWS, and then the replication would have been from AWS into Equinix. Okay, so the procedure remains same. It's just the direction of the replication and the use cases attached with that message. Now, in this case, since our source is Equinix and target is AWS, what we are now going to do is basically simulate a failover where you know that our source volume has the data set called as a table called as car, and let's validate that so that I can show you. .110.204.111.56, I think. Oops, sorry. Blunders like this. Okay. Let me remove this part. So this is the Adminer web UI for the Adminer pod running on EKS Anywhere. And we are going to open the connection to the MySQL server running on EKS Anywhere and validate once again the data set that we have populated at this end. So you can see that there is a CSI test database, and there is a table card, and there is some data in that. Okay, I'm going to just delete a couple of entries just to make sure that this data is, fresh enough. What I mean by that is 41 rows now in the table. And when I've written this particular change, this should have persisted onto the PowerFlex in Equinix. Okay, the replication should have been instant onto the other end, which is on the PowerFlex over AWS, which means the volume that is there in the target that is on PowerFlex over AWS should have taken these changes by virtue of the replication. Okay, and now that we have created the EKS cluster, also we have done the CSI integration. When we mount this particular volume or build a PV from this particular volume on AWS end, we should be able to see the same data at that end. Okay, now in order to do that, let's simulate a scenario. Okay, and I'll show you how do we do that. This is the PowerFlex 45 AWS end, and this is the Equinix end. So let me log in here to refresh the browser a bit. Okay. Now, in order to simulate or actually perform, not a simulation, but actually do a failover, I can go to the RCG under which my volume pairs exist. Click on the volume, the RCG. And like I described earlier, there are various actions you can do. One is I can test a failover. Okay. So it will just kind of, do a test of that, those, attributes. The other is I can actually do a failover. So when I do a failover, let's click this. Let's apply the failover. Okay. Now it does give you an indication that failover before stopping the application may result in the IO error, which is true, right? I mean, let's continue as is with the defaults. And you can see the failover for the replicate RCG is successfully applied. And by virtue of that, you can see that the replication status is stopped by user because we have invoked a failover. And the state of the RCG in a switch is in a switchover state. Okay. It's still in a consistent position, but the state is in a failover state. Let's say that. Now, what it designates is that now I can, in the remote system, if I look at the RCG, you would see a similar status. Inside of this is my volume pair. Okay. And this volume at the AWS end, which has been replicated, should have taken those changes that we just did by deleting the table entries. Now I can consume this volume to build a application set on the EKS cluster. Okay, because now I have this volume in a state of failover, and let's say we have the DR invoke, we can create an on-demand business continuity by leveraging this data set now, or this particular volume, where I can now start to read and write from this volume basically. Okay, so let's try doing that. How do we do that? First, let's identify the volume ID. So you can see here that there is a volume ID associated. Note that I'm at the AWS end. Okay, let me take this volume ID. First things first. Okay, let me paste it here. So this is going to be my volume ID. Now I'm going to go back to my kubectl here. Okay, I will create a YAML file here from this template that I have it on my GitHub repository. Let's see what it is. So I go to EKS Anywhere. I go to MySQL standalone, PowerFlex, and there is a MySQL PVC target cluster. The source cluster as such is a dynamically provisioned volume. Okay. The target cluster volume, however, needs to be resurrected from a volume handle, which will be the volume ID. Okay. Now, while I will get into those details, let me copy this particular file. Let's create pvpvc.yaml. I mean, just a name. And let's paste it here. Okay. Now, note that I can, depending upon what I want to do, I can either create it as a read-only volume so that no further changes in terms of application consistency occurs. So I just keep reading whatever data I have, or I want to maintain a true business continuity where users are not impacted and they can still access both read and write onto the database, right? So I can do either one of them. So let's create a true one, which is read write once, so that the volume can be written and read from actually, right? So what needs to be changed, like I said, is the volume handle. Now this volume handle needs to be of the volume that has been replicated and now is in a state of failover. So let me put this volume ID here so that I get things going. Okay. With that, let me create, sure if I've created, let me create the namespace demo. Okay. So now the demo namespace has been created, in which we will create this persistent volume claim. So let's apply this. Okay, one additional thing, let me just make sure that you get it, is that you can see that the CSI that is going to be used for this persistent volume is on the PowerFlex system. Okay. And you can see that the storage class also is PowerFlex SC, which means that this particular volume will be derived out of the storage class, which is linked to this particular PowerFlex driver, actually CSI driver. Okay, so let's apply this particular kubectl create -f pvpvc.yaml. Okay, as we can see that the PV and the PVC have been created. Let's validate this. Okay. Okay. So now both of these have been created. Now, as a result of this, we can create our MySQL database, which will read or which will be mapped onto this particular, the volume mounting will happen from here actually, right? This particular PV and PVC combination. So in order to do that, let me pick up the MySQL template. Sorry. Let's just take the same thing which we have deployed as a template at the Equinix end. It's just a template. It does not have any other thing except the fact that it has the reference to the MySQL or the PVC claim, right? So let's take this particular template and MySQL.yaml. Sorry. and put it here. Okay. Let me validate if everything is intact and there are no mistakes that I don't intend to do here. Okay, so you can see that the claim name is MySQL-PV-claim. Let me save this. You can see MySQL PV claim is the PVC claim that we've built at the AWS end also. And let me create this particular mysql.yaml. Okay, let's check out the pods. For MySQL. Okay, let's wait for it. While this happens, I will also build the adminer deployment. So let me grab from here the adminer file. You can see that there are two adminer files here. This adminer file is with an internal NLB. Now, NLB is purely available at the AWS end. If you recall, at the Equinix end with the EKS Anywhere cluster, our adminer pod was exposed through the load balancer, which was supplied by MetalLB. Here, in the case of AWS, we are going to use the internal NLB to expose the adminer pod. So let me take this particular here, nano adminer AWS YAML, for example, and let's paste it here. Okay. And also apply this particular file here. Okay, it consists a definition called as demo namespace definition, but it's already created for us, so not a problem. Now you can see that both the pods have been successfully deployed, which means that, in summary, let me just show it to you again here. So, which means our MySQL pod should have the persistent volume claim and the volume attachment successfully done. Okay, so we can see that the volume called as the PV, called as replication target, manually whatever we have named it, that has been successfully attached to this particular pod, to the claim name, which is called as MySQL-PV claim. Now, as such, what we realize is that the CSI integration is working between EKS and PowerFlex over AWS. That's working because we are able to do this business of persistent volume. We've been able to mount a volume from PowerFlex over AWS into this particular EKS cluster for the MySQL pod in the demo namespace, and everything looks to be hunky-dory. Now, let's validate this. Get pods -n demo. Let me validate this is working. I have sometimes seen some challenges with regards to NLB, internal NLB. If that seems the case, we might have to do a bit of troubleshooting. If not, we will continue. I can see that the IP or the load balancer URL that has been received for the adminer pod, is this. So let me copy this again. and try to access it here. Okay. While this happens, just give me a minute. Yeah, so when this was happening, I was just validating if the targets were up for this load balancer. And since it takes some amount of time to make sure that happens, I can see that the adminer interface for the adminer pod, which is on the EKS cluster in public cloud, is up to this particular NLB URL. Yeah, you can see this URL is the NLB URL. And this one is my adminer pod on the EKS anywhere cluster exposed to the Metal LB pod or Metal LB load balancer. Remember, we deleted some of the entries here, and we assume now that the replication would have happened. About 41 odd rows should have been replicated onto the target volume through the from the PowerFlex in Equinix to PowerFlex over AWS. We created the MySQL pod, we mounted this particular replicated volume, and now we will log into the adminer and try to validate this particular data set at the AWS end. So MySQL root. Okay. So what can you see here? Some good news, which is you can see that the replicated volume has the database called as CSI test. Okay, so this particular database CSI test has been replicated at the target. I'm trying to intentionally draw focus onto source and target so that you know that the replication is working. Let's click into this particular CSI. We can also see the table car. Yeah, which means that the data set should be also there, and the moment of truth. Yeah, the moment of truth would be that 41 rows. So this is also 41 rows. Recall this was 43 rows and we deleted a couple of rows. Real-time replication replicated onto a target volume here, and we see the 41 rows, same thing. So that kind of concludes what we would say as a, in my opinion, a very powerful expression in terms of how can you create a substrate which is based on a unified or a consistent storage technology across two, I would say, distinct infrastructure providers. One is a Equinix and one is AWS, right? And in that, we have placed our PowerFlex storage, which again, from the first video, if you recall the introduction from Simon, talks about how powerful this platform is. And in this context, we've explored the capabilities of building a hybrid data plane. And note that the PowerFlex platform can not only work with physical machines, but also with virtual machines. Okay, so you could have virtual machines at both ends and replicate. And also like how what you have seen now with containerized workloads. So you have EKS anywhere and EKS persisting, their data, replicating, and the story is mounting here. Now, we can go on and on in this pursuit to evaluate many different feature sets that PowerFlex as such can bring into the mix. We could do, for example, migrations. You could also look at some of the replicas for doing offline, transactions as a read-only system and whatnot. Now, you could also think of, the point is clear to you. but just kind of highlight it here. You could also look at reversing the entire. You can see this state. You can just go, and sorry, this, and you can do all kind of funny things here. Reverse the whole thing, restore. I think this is standard, beyond this. So again, I would like to thank all of you, and I hope you have enjoyed, like I said, the practicality of this whole demonstration. I know sometimes it can get a little intense since the technologies are new, and it can get a little comprehensive in that sense, right? But my intent has been to give you a very clear picture of how these technologies work, A. B is how you can correlate it to different use cases that you see inside of your environment, right? And then build upon those, exhibits as business demands actually. Okay. With that said, thanks again. Enjoy. Thank you.